We left off at the end of part 5 of this video with the question of how to create a chamfer along the outside edge of this workpiece. And of course, if you have a mini lathe, an obvious way to do it would be take the workpiece over to the lathe and stick it in there, and it would be a quick and simple job. But let's assume that we don't have a lathe and we need to solve the problem using just the tools we have at the mill. So if you start thinking about what could sweep along this outside edge, one of the first things that occurred to me is that's very similar to what a boring head does. So let's take a look at that. Boring heads, as you might guess, are typically used for boring holes, usually holes that are larger than you can drill with a drill bit. But in this case, I thought we might be able to use the geometry of the boring head to sweep around this outside diameter of our workpiece. So I've put a typical boring tool in place in the boring head, but of course the cutting edge normally is turned so it's facing outward because you're cutting on the inside diameter of a hole and enlarging it as you make successive passes. Boring heads have a calibrated micrometer screw, and by turning that screw you can move this lower silver portion in or out relative to the center of the boring head and therefore increase the diameter that is bored. If we rotate the boring tool around so that the cutting edge is on the inside, it almost does what we want. And if we sweep that around, you could see that it would potentially cut along that face. This is the normal forward direction for the mill, which is clockwise when looking down on it from above. But this mill, of course, has a reversing button, so you can sweep the other direction. So that would almost do what we want. The only problem is that this cutting edge of the boring tool is angled inwards. So instead of cutting a bevel along the top edge here, it would actually cut a little trough down below. If you had a bunch of old boring tools, you might take one and mount it in a vise or some such thing and bend the shank a little bit, maybe heat it up with a torch and bend the shank so you could change that angle. So if you had one to sacrifice, that might be a way to get the job done. And in fact, somewhere around the shop, I have one that was bent during a job that probably would work, but I wasn't able to find it. So we'll have to come up with another solution. The tool mounting holes in this boring head are for a 1/2 inch diameter tool bit, and I found in my drawer of tools this specialized drill bit for chamfering. And I think this was actually another tool that was given to me for that project that we've been talking about. And I think the purpose of it was to chamfer this edge here, which again is somewhat similar to what we're trying to do, except that this is the inside of a circle and this is the outside of a circle. So after mounting this tool in place of the boring bar, it looks like it has the right geometry to get the job done. So I'm going to rotate it slowly just to see how that looks. And of course the spindle has to be exactly over the center of the workpiece for this to work. If it's off by even 1/1000th, then the edge is not going to look very good. I think I'll keep the spindle stopped until I get very close to the edge there so I can just make some minimal adjustment. In fact, I think I might touch off on that edge. Okay, I'm touching off now. I'm going to zero the Z-axis on the DRO. And now I can back off just a little bit, and I can use the DRO to guide me down. I'm going to speed it up just a little bit, but I don't need to go very fast for this. So I'm currently reading about 300 RPM, and I'm now very slowly bringing the head down using the fine feed control. Well, I was starting to get a little bit of chatter there, so I decided to back off and think about this some more. And it doesn't seem to be cutting very evenly. So you can see it sort of did chamfer this edge here, but it's not a very good looking clean cut. I'm going to try once more. I've angled the, I guess we'll call it a drill bit, back just a little bit so it's coming in at a slightly different angle than before. We'll see if that makes a difference. Well, not really. All right, well, that doesn't seem to be a very good solution, but I'll think about it a little bit more. Maybe I can find a way to make it work. I found this shop-made tool ground from 5/16 inch tool stock in my drawer of miscellaneous tool bits, and after I reshaped it a little bit on the grinder, I think it might be able to do the job that we need to do to chamfer that edge. But there's a slight problem because this shank is 5/16 inch diameter, but the holes in the boring head use 1/2 inch diameter tools. So I decided to make a sleeve on the lathe to adapt this tool to fit into the boring head. With a few minutes work on the lathe, I made this sleeve. These spiral grooves are left over from some former life of this piece of stock, and this is drilled out to one size under 5/16, which is the diameter of this shank, and then reamed to 5/16. So the idea is to insert the tool shank into here, and I can clamp it down. But in order to clamp it, I'm going to need to put a slit down the side of this so that it can be compressed by this screw. I'm going to use this shop-made slitting saw tool. The arbor is shop-made. The blade itself is an inexpensive blade available at Harbor Freight. I have the slitting saw arbor mounted in a 1/2 inch collet and have the slitting saw now in place. So now we have to line up the slitting saw with the work. I have the sleeve held in the right-hand side of the vise jaw, and I have it offset so that I have clearance to cut through this side with the slitting saw. I have the top of the sleeve just a little bit above the vise jaws so I can lower the saw down and touch off on this surface to get my zero reference to find the midpoint. Over here I have a little, I guess you'd call it a mini lab jack or a mini shop jack, and this is just an adjustable screw thing that I made in the shop, and I have these in several sizes, but it's here just to offset the pressure on the vise jaw. So I clamp this piece loosely, and then I turn this to fit in the jaw, and then tighten them both down together. That helps to keep the vise jaws parallel when they're tightened down. I have the slitting saw now lined up with the midpoint of the sleeve, and we're ready to start cutting. And I'm going to use a pretty low RPM because this is a large diameter cutting tool, and I'm putting a little Tap Magic aluminum on there, which will help it to cut more smoothly and keep the chips flowing freely out of the groove. So I'm going to run the saw only at about 300 to 400 RPM. I've got it at 300 right now, and I think that's probably turn it up to about 400. So I'm going to ease the tool into the side here now. And I'm going to start advancing it slowly. Adding some more cutting fluid. Okay, I think that will do it. Let's take it out and clean it up and see how it looks. Since I had to remove the collet block and the workpiece in order to use the slitting saw, I now have to use the wiggler once again to find the center of the workpiece now that I have it mounted back in the vise. The wiggler comes with several different types of probes, I guess we'll call them, and this one is a sort of a ball end probe, and this is exactly 0.250 or 1/4 inch in diameter. I have a theory that the ball type might be a little bit more accurate in finding the edge because it has more mass and therefore tends to swing out more readily when it reaches the center point. But when we work on the mini mill, a lot of times there's very limited space, so having the other smaller tip is also very useful. Because we are measuring on both sides, the diameter of the tip of the wiggler doesn't even factor in. You just take half of the two readings and then zero it out. You're at the center. Now I have to repeat that for the y-axis. Well, there we are after having centered in both the x and the y-axes. The boring head is a pretty long tool, and in order to get it up into the spindle, I had to move the workpiece off to the left side here to give me some clearance. But because I have the DRO, of course, I can get right back on center without any problem. I took the reamer and ran it through on the lathe after cutting the slot, in order to clean up any burrs from the inside so that our tool will fit up in there. Now we'll stick this up into the boring head. And I need to turn it so that the slot is perpendicular to the force of the screw so that it can close down on it. I want the cutting edge of the tool facing inward. And now we'll tighten that whole assembly down. Hopefully it will stay in there tightly. Feels good. That looks pretty close to what I want. Let's give it a try. I'll touch off first. I have the tool just a little bit above the surface of the work now. You can hear it starting to tick a little bit as it contacts the work. And I'm feeding down very gently. Well, it's not chattering too much, at least not as much as the boring tool was. And really the purpose of this whole exercise is to demonstrate the versatility of the mini mill and how with a little bit of creative thinking you can get a lot of jobs done that might not be immediately obvious. And this also, of course, gave us an opportunity to look at the use of the slitting saw, the collet, the boring head, and the wiggler, the DRO, and some other things along the way. I wasn't satisfied with the quality of that chamfer, so I decided to use the indexable end mill again and do another pass on this. I used 2,000 RPM this time and a somewhat slower feed, so the surface finish is even better than before. Before I cut this off to a 0.5 millimeter disc, I'm going to go ahead and countersink these 4 holes here for the screw heads. I decided I could do a better job going ahead and countersinking those holes while I have everything set up on this side, because when I cut it thinner, it's going to be hard to get the new face exactly parallel with this face once it's flipped over in the collet, because it's a relatively short piece of metal to grip onto. I also wanted to try once again to chamfer this outer edge using this, well, it's a chamfering bit, I guess. This time I'm going to try using a very slow speed and see how that goes. So I'm lowering the head down using the fine feed. It's just starting to touch now. Alright, well that looks a lot better, and I think I'm going to just leave it like that. Another tool that I received for the project was this small chamfering end mill. I'm going to use it to countersink the holes for the heads of the metric screws. The smallest standard countersink that I have is quite a lot larger, so I think this smaller chamfering end mill might do a better job on these little holes. I consulted a chart on the internet, and if I read it correctly, the countersink depth for the 2.5 millimeter screw is 2.5 millimeters. I'm going to feed using the 3-spoke hand wheel. I'll be watching the Z-axis DRO. Well, that doesn't sound good. That's not what a countersink should sound like. So I'm going to revert back to my other one. That's better. I'm going to go even lower though. Alright, well that's looking better. Now that I think about it, I normally run countersinks at very low speed, and I guess that's the reason. My test screw is 10 millimeters long, but my hole is only 8 millimeters deep, so this is a 6 millimeter, and it fits in there very nicely. I decided to try again with that small chamfer end mill with a slower speed. Still did a bad job. Got a lot of chatter on that hole. Well, I guess it really is intended only for chamfering and not for countersinking. I also discovered that these screws are not very magnetic at all, so they're kind of hard to get out of there. I'll try a trick I sometimes use for retrieving non-magnetic screws. This is just a stick with a blob of red wax of the type that's used to pack Dutch cheeses. It works pretty well for this type of situation. I'm going to try to clean up that chatter on the surface. Well, that didn't help really, and I don't want to risk making that hole too large, so it'll be covered up in any case, so I think I'll just leave it. I'm going to put a little cutting fluid on these other two holes, and we'll go ahead and get them done. Well, that was a lot better. Well, other than that one that has the chatter marks, they turned out pretty well. You can't learn things unless you try things, right? So sometimes it works out and sometimes it doesn't. You can see that the last two countersink holes are deeper than the first two. And I think what happened is when I changed back to the other type of countersink, I did not get the 0 point set accurately and I ended up going a little too deep. But this is a demonstration, so things happen sometimes. I'm getting ready now to slice off the top of that whole workpiece at a depth of, I got it about 7.7 on the DRO, and eventually I'll reduce that down to 5 or 6, I guess, when we get it flipped over in the collet. Let's get some cutting fluid on here. Now this is going to be a pretty deep cut for this little saw, and we can't get all the way through because the diameter of the workpiece is greater than the radius of the saw. So we'll have to go part way through and then reposition the work and come in from the other side. I'm only going to use about 300 RPM. We'll need to periodically add more cutting fluid. Even that sounds a little fast to me. I'm going to go down to about 250. We're going to be taking a pretty deep bite as we get farther in here. There's another way we can go about this. We can come out here and then advance the saw in a little bit and then make a pass this way. I think that's going to be a better tactic. Now we're cutting in the Y-axis. As you can tell from the sound, it's not cutting evenly, so one area of the saw is probably getting all the wear on the teeth. Well, I wanted to demonstrate that we could get at least halfway through, which I think shows that the job can be done, but it's slow going, and it's probably taken me about a half hour to get this far. I'm cutting at 350 RPM on the spindle and taking 1 millimeter per pass, so we have to make at least 25 passes to get all the way through. There's an old saying that discretion is the better part of valor, but I'm going to interpret that to mean I should take it out of here and cut it off on the bandsaw, and then we can get on with the project. So here's what we have now that I've removed it from the collet, and you can see the cut there. I'm going to take it over to the bandsaw, cut it below that point. Well, that took about 3 minutes versus about an hour or so on the mill. Here's our workpiece after cutting it off on the bandsaw. Then I turned it down on the lathe just to clean it up. You can see this is where we cut through with the slitting saw. We didn't get quite halfway through, but just about. Now I need to mount the workpiece in the collet so that we can finish this rough surface. But it's difficult to get it to seat in there exactly square because it's such a short workpiece. So I'm going to use this shop-made device called a collet stop, and these are also available commercially. But it has a flat surface here that will butt up against the workpiece and force it into alignment. So with the collet still loose, I'm going to gently tap the workpiece down into the collet. And I'm using this soft face hammer from Harbor Freight. And now we'll insert the collet stop and use it to push the workpiece out. The collet stop threads into the back of the 5C collet. The 5C collet has both internal and external threads, and the internal threads are just for this purpose. Now that that's snug in there, I can tap on the end of this bar. That will push the workpiece out of the front of the collet while ensuring that it's square to the center line of the collet block. Now I'll move the collet block over to the milling vise and use a spanner to tighten up the collet. Now that the collet's tight, I can remove this collet stop because this part would be in the way of being able to mount the collet block vertically. I've used the DRO to bring the workpiece back on center with the original settings from earlier, and now I've brought the indexable end mill down onto the top surface and set the Z-axis DRO to 0. Now we'll back off to clear the edge of the work, and we'll set a cutting depth of 0.5 millimeter. Now we'll lock the Z-axis and turn on the power. I'm going to go with about 1500 RPM. You've probably noticed at other points in the video how quickly the spindle stops, and it's done electronically. So the only thing remaining now is to countersink these 4 holes. One minor issue is that the holes are no longer aligned with the X and Y axes as they were originally. I'm just going to hold the collet block freehand to countersink these holes because it can be done at very low RPM, and it's a pretty simple operation. And as long as you keep your hands out of the way, it's pretty safe. I was taking the workpiece out of the collet thinking I was done. Then I realized that I still needed to chamfer this outside edge. So we're back in the vise again, and I need to use the wiggler to re-establish the 0 point, at least in the X direction, since the collet is not in the same position that it was before. This is an example of where the smaller wiggler tip is required because there's very little surface here to make contact with. I now have the base mounted to the precision fitting that we started with. It looks pretty good due to the accuracy of the DRO. Everything lines up perfectly. Pretty good considering these were made on 2 different machines several years apart. So as I mentioned earlier, the countersinks aren't perfect, but for this level of demonstration, I think they're adequate. And the goal here, of course, was to demonstrate just what the mini mill is capable of. So you came for a product review and you got a whole tutorial instead. But that's how I roll here. Yeah, from the very outset when I created minilathe.com back in 2000 until now, my goal has been to introduce machining to younger people and get them interested and excited in it, and hopefully get them to take it up as a hobby.